follow. Let's go back to the basic sciences and they work with us here. How could it happen? Not happen on secondary prevention, not happen in acute coronary disease, but happen in primary prevention. What is going on? And then what we saw that we had to add into the mix is that if you just looked at older women, they in fact look exactly like men. So if you did it over the age of 65, here was your benefit on stroke, and here was your benefit on myocardial infarction. But I still had to worry about risks and benefits because these 44 fewer events caused 16 additional hemorrhages. So is it enough to be able to recommend it? The AHA guidelines said anchor to 65. Do something different if you're under or lower 65. I don't agree with that because I never set 65 as my cutoff in advance. I think 65 is we finally just had enough events, enough myocardial infarctions, since stroke occurs more frequently at younger ages. We finally had enough heart attacks for us to be able to look at that definitively. So what comes from this when you kind of see the differences? This is never going to be completely resolved, meaning that primary prevention is just never going to be the same as secondary prevention. It's always going to be an individual clinical decision where we sit with the man and we sit with the woman and we look at his risk factors for heart disease and we look at her risk factors for stroke and we look at both of their risk factors for having an adverse event from the taking of aspirin and we figure out how that risk to benefit analysis goes because there are discrepant findings between the two. And I never started this study thinking that I would be doing it to find something different. But what it does underscore is the importance in looking at subgroups. They're large enough, important enough to us to make sure that there are not differences between the groups. Now, beta-carotene in one slide, I think we remember this one. This was sort of the beginning of what I thought it was my time when I felt like that there wasn't a Santa Claus or a tooth fairy anymore. Things weren't going the way that they were supposed to. We knew that people who ate their 5 servings, 7 servings of fruits and vegetables had a lower risk of cancer as well as cardiovascular disease. We knew a mechanism. They were rich in beta-carotene, those fruits and vegetables. We understood that beta-carotene was an antioxidant. There was no suggestion of harm, either overall or in the subgroups of smokers, non-smokers, or anybody else. So trials began completely appropriately. But they showed no benefit of beta-carotene on cancer prevention in well-nourished populations. Again, unexpectedly, they saw harm that had not been seen in the observational studies. With parrot, HEDC saw harm in lung cancer incidence and mortality among smokers. The physicians' health studies didn't see that. The studies did. And there was no idea at that time of a mechanism by which beta-carotene could be increasing risks in smokers. And so that went back to the basic researchers. We learned a lot since then. That raised questions about the role of specific nutrients in cancer prevention, nutrients versus food, and trying to see whether we could look closer at the observational studies to try to see a better relationship. Maybe food wasn't beta-carotene. Maybe that was the wrong nutrient to have picked. So then vitamin E became in vogue. And the advantage of vitamin E was because most of the vitamin E that was shown to be beneficial in the observational studies was supplement level, not food. So it wasn't a matter of looking at the food and saying, well, it also seems to have a lot of vitamin E. Let's look at that. You were really in supplement level, and so it seemed to be more direct. But again, those who had vitamin E supplements might be systematically different from those who didn't. How How do you know it was those who were eating a high amount of vitamin E that it was the vitamin E and not something else? So again, a very logical progression from the observational studies to the trials. And the trials that had been done were secondary prevention, not long enough, not primary prevention, meaning that they were very informative for what they were looking at, but we still didn't know if there might be some effect of longer duration.
To first give you sort of a historical view of how we got into studying clock genes. And then I'd like to turn to a few more recent examples of how we study clock genes and what their functions might be and how the system is organized. And so today, as a neuroscientist, it's a very exciting period because our ultimate goal is really to understand behavior and disorders of behavior in the brain. And we're, as you know, undergoing a revolution in both genetics and genomics. And so the combination of neuroscience and genetic approaches has really opened up a number of approaches to understanding behavior. So our interests have been to identify genes that ultimately control behaviors and behavioral disorders. And so I wanted to do today is to try to show you an example of the circadian system in which we can work at all these levels of organization, starting with behavior, working backwards to identify genes, and then to use those genes to study how circadian rhythms are generated in cells and in circuits. And one of the themes of today's talk is really that the cell is really the fundamental unit of the clock in the body, but that the organization of these cells into circuits actually transforms this information to control behavior. And so it is important if we want to ultimately make links from genes to behavior to understand these different levels of organization. And the circadian system is really a beautiful example of this, where, as I'll show you, we have identified a number of clock genes involved in this pathway. Cells and circuits, primarily in the suprachiasmatic nucleus of the brain, are involved in generating circadian behavioral rhythms, but also to regulate physiology and metabolism. And alterations in physiology and metabolism ultimately could lead to or have impact on disease and pathology. So in humans, sleep-wake is really the most obvious rhythm for us, and it's clock controlled. This is a very old experiment done in the 1970s where a medical student volunteered to go into isolation in an underground bunker at a Max Planck Institute in Erlangen-on-Dex. And so he's living in an apartment with the door open, and this is a wake-sleep plot. He's awake when it's blue, he's sleeping when it's yellow, and the arrowhead shows the low point of his body temperature rhythm. And each line is a day. He's living in the apartment with the door open until this point. Then they close the door and isolate him from all temporal cues. No clocks, no TV, no radio. He has 24-hour room service. And what you see is that his sleep-wake pattern continues, but that the timing of it drifts to later and later times of day. Okay, so that by this day here, he's waking up at midnight instead of 8 o'clock in the morning here at the beginning. On this day, the door to the apartment was opened again, but he continued to live in this apartment. And you see a second feature of these rhythms And that is, he goes back to a regular 8 a.m. wake-up time and going to sleep around midnight. And his period length is now 24 hours. It's synchronized to the environmental cycle. So rhythms are generated internally by a clock in our brain. But the environment plays an important role in synchronizing our rhythms, both to control the period length, to make it 24 hours, but also, importantly, to control the phase. So we as humans are diurnal. You see that he goes back to being diurnal, waking up at 8 a.m. Now, there's a curious feature in this record here. Why is he over here at 8 a.m. on this cycle as opposed to 8 a.m. over here? It turned out, while he was in isolation, since he was in there a long time, he actually lost an entire day. He went through one fewer biological cycles than the number of real days, because he's waking up more than an hour later each day. Okay? So those are the features of rhythms. In people, light is the major synchronizer of our rhythms. There's a specialized set of photoreceptors, a new class of photoreceptors in retinal ganglion cells that mediate this information. They project into the hypothalamus into these two yellow wing-like structures, which are called the suprachiasmatic nuclei.